So here we would like to present the first tutorial, which is about training elasticity energy functional for using a TensorFlow. So by now you should have access to the Jupyter notebooks, and there are other handout material provided in the short course that provide a fresh review on how to use the Jupyter notebooks. Here, we will use a simple way to doing it is that we're going to launch the Jupyter notebook with the Google Collaboratory. So it's very simple. So if you click on the Jupyter notebooks, we should have extensions of IPYNB, and we will simply open with Collaboratory. So once we log in, we should see the descriptions and the code that I put together. Here you can see you can connect the Jupyter notebook to on the cloud machines or to the local. And in some case, if you haven't run the code before, you will have to connect it to somewhere, or at least connect it to the Google Cloud. I would suggest the student attending this course to simply using the Google Cloud. The exercise or the tutorial that we generate are actually not extremely computational expensive, and should be able to execute on the cloud. So once you connect it to the host, you will see the RAMs and then the drive. And for the free Google engines, you have the RAM of 12 gigabytes to be used, and then the depth and then the hard drive you can use is about 100 gigabyte. So that should be enough for the task. So here we would use the supervised learning for the energy functional to start the first tutorial. We picked this example simply because training a scalar energy functional is actually very common for a lot of engineering tasks, and it also could be a good way to introduce what is supervised learning. So in general, supervised learning meaning that you have some kind of input and output that are actually obtained from external source, which we treat it as a ground truth, and then you using this to train a computer algorithm to predict the future events. If you're giving a new input, how do and how to map it into the output that actually consistent with the previous input-output observations. Okay, so the part that really black box interpret operations, or at least can be treated as a black box operation, is the tuning of the neural network. Okay. So here we would actually finish everything in a script, and including the data generations. So I just want to provide a fresh review for those who are not familiar with the hyperelasticity energy functional. A hyperelasticity energy functional is basically scalar functions that take the tensor value of a string or some invariance of the string and output the energy. So this is actually nice because energy is actually a scalar, a non-negative scalar. So in the invariance case, I will actually show an example where we are assuming that the energy functional is formulated for small deformation for simplicity. And there are only two variables: the volumetric strain measure and the directory strain as an input. Okay, in both cases, they are actually scalar. They're the scalar that are actually coming from a tensor, so it also simplifies the problem. So essentially, in this energy functional, we have two scalar as an input and output another scalar. So what actually make it interesting is that if you take the first derivative of it against the volumetric strain and the directoric strain, we can get the directoric stress and the mean stress. And then because we are actually assuming that the material is isotropic, we can the directoric strain and the directoric stress would have the same directions and vector, and that would help us assemble a Cauchy stress. Hyperelasticity energy functional functions as the following. If you take the first derivative of the energy functional against the strain, we will get back the stress. If you take the second derivative of it, we will get the tangential stiffness matrix. And here our focus is based on only on elasticity. While the same principle can also be allowed to train energy dissipations or other entities such as a damage parameter, etc., etc. So I will first talk about generation of the data that has nothing to do with machine learning, but I just want to emphasize that we just generate a linear energy functional, which is actually redundant in the sense that you really don't need a machine learning. But the scoop is here, and if you actually have your own data of stress strain curve or the energy and stress strain relationship, you can basically replace this set of the data. This is also the advantage of using the Jupyter in the sense that you can run through the whole process of how this thing works, and you can actually make any changes. If you want to make change, what you can do is that you can save a copy in your own Google Drive, and you can actually make any change as you see fit. And you can also actually pin the versions and say the revision history if you actually if you want to compare or go back to the later version. So this is optional, so I'm not going to go over in details, but basically we create a ground truth data from analytical solutions. If you like, you can also add some noise in between, maybe add a random noise there, or actually change it to another data that you obtain from molecular dynamics or from discrete elements, or from a direct numerical simulation using finite element or material point. The point here is not the type of the data, but just a way to generate the data. Okay, once we have the data in this particular case is stored in a point cloud. So let me show the code here. And then we leverage the automatic differentiations to generate the data. And this is also a nice capacity. This is actually also a nice thing in the NumPy, is that you have the automatic differentiations that you can use both to generating the data and to check the data. Okay, so this is actually coming from here. Okay, so in this Python code, we actually create a space that actually have a 50 by 50 structural grid. So what it means is that we actually parameterizing we have an equally spacings point cloud on the parametric space of the volumetric strain and the directoric strain within this range minus 0.2 to 0.2 and 0 to 0.3. This is actually because the energy functional in small deformations, so a very large number will probably make it non-valid anyway. So I think this is pretty simple. We actually define the modulus, shear modulus, and we actually create an energy functional as the ground truth. Again, the data generation part is actually redundant, and I would encourage the student to try to replacing this data into something that are actually coming from a direct numerical simulation. But here it is. So our focus is on the Sublet training, which means that when we construct the loss functions, we would actually try to minimize the discrepancy between the predict energy and the actual energy benchmark, but also the stress, and if possible, if the second derivative is also available, the tangents, the elastic tangent operator. But here you can see that it's not necessarily a difficult task because we can simply using the gradient to generate the extra data. So one thing that are also beneficial for the Sublux training is that for the same discrete point, the Sublux training can give you more dimensions of the data. So what I mean is that for the same amount of the volumetric string and directoric string, you can not only use the energy to create an energy function node, but you can also use the stress and the tangents to give you a better idea of the shape of the energy function node in the parametric space. You can control the derivative, which is important to kill off the oscillations, and you can even controlling that the tangents have to be positive definite, which is important for solid mechanics problem. Okay, so here in the first part of the data generations, you may want to pay attention on the calculations that using the automatic differentiations that could be very convenient and often used in a lot of machine learning tasks. Now, we will present another implementations or another script that are based on PyTorch. But here, the machine learning library we use is TensorFlow. So and then those are the user suspect that we need to import. So the TensorFlow library, and of course all the important ingredients, the model itself, which actually tell, and then the layer. So in the layer, you can control the type of architect. Usually the most common one is a dense one, which is just a fully connected neural network. We also add a multiplier network. The details of it could be found in the paper by Venice and Sun, which is actually me. And this is actually invented to allow the RU, LU activation functions. This is just to create a multiplier layer in order to increase the degree of continuity for the learn function, such that it can we can obtain the tangents in a smooth manner. And also we need to drop out layer. This is actually pretty classic. And it could be used to regularize the neural network. What the dropout layer did is that it deactivates part of the neuron and then try to learn the problem in a based on the dropout way, and then it actually have regularizing the problem. Again, the nice thing about using the Jupyter Notebook in this manner is that when you click on the terminology, and that is actually thanks to the good documentations of the TensorFlow, you can actually see the definitions. This is also a great way to learn what is going on. The TensorFlow library already explain the class in the menu, and when you click on those variables, you can see the definitions. The dropout, you can find it here. The custom multiplier layer is probably you can find the code here. You can find the explanation here. The dense layer, etc., etc. Okay. And then the optimizer we use is Adam algorithm. Again, I think most of you are familiar with it. Adam optimizations basically add a stochastic component on the gradient descent method. This is actually important to overcome the local minimizer and then help find the global. To balance the need to optimize locally rather to exploring a good choice that are actually far away from the local minimizer. So and then this is actually, and then the mean square error, I think is very intuitive. Basically, in most case, the criteria or the loss functions or the thing that used to measure the loss function is actually not necessarily just a scalar, but most likely measure as a vector. The mean square error basically tells us the square root of the inner product or whatever things that we are measuring. So here, the second sections. After the first sections is about preparing the data and import the right library. So by now we have made all the preparations, and then we are going to start to build the neural network. Okay. So here we would actually do a few numerical experiment. We would actually have a fully connected hidden layer with 100 neuron, and then use the ReLU activation functions. And then we will add a multiple layer twice to increase the continuity. Notice that the ReLU activation function is a piecewise constant continuous activation function. They probably look like something like this. So, and then there's a sharp change on the first derivative. So inherently, those are not necessarily ideal choice for Sublux. Sublux training, because the Sublux training require a smooth numerical derivative that you can obtain. But one thing to bypassing it is to use the multiple hidden layer that we actually invent. Or another possible choice is to use the hypertangent activation functions or any activation function that can give you the continuity. However, one thing that that are actually important to know is that for different activation functions, if you actually try to build train a neural network before, you will see that it will have a very different learning way. So sometimes, in particular, for the more exotic activation function that have less theory backup to it, the training could be potentially harder, and it's actually not easy to find the hyperparameter in that case. So here, there are a few things that appear to be quite random. The number of neurons, the number of layer, and then the architecture of the layer. So those choices are called hyperparameter. And then unlike the actual parameter like a Young's modulus or Poisson ratio, hyperparameter are basically a different way to constitute an architecture. And there is no known, in most cases, there is no known predefined set of parameter that can optimize a specific task. Very likely it needs to be done in try and error. In TensorFlow, there are some tools to tune the hyperparameter, but again, the more complex or the more general you want to search a hyperparameter, the more expensive the training is become. Nevertheless, this is a hidden cost that are very important to consider. So my personal experience is that use activations function like ReLU that or hypertangents or other things that have more established background or easier to train, and then occasionally for specials problem there may be a need for more exotic thing, and then you also need to think about what is your architect. Okay, so in general, of course, you can imagine that, I think there's a spell typo here. Imagine you can easily imagine that if I put more neuron, I can probably approximate more complex equations. But things that are not so clear is whether I should make more neuron per layer, or I should make the layer more depth, or vice versa. Anyway, so this will require some try and error. So this is also the interesting part that I would actually ask the student to try out a few more things. Another very important thing is how to initialize the neuron weight. So a neuron actually in a simple feed-forward neuron, basically we control the bias and also the weight in order to get the optimum response. But before we actually provide any training, we need to initializing it. Things that if we actually find it work out, and we're not going to talk about too much about the theory background of it, is actually these initializations. So in TensorFlow, the training is actually the building of the neural network architecture is very, very simple. You can see I want to build 6 layers of neuron with 100 fully connected neuron in the first layer, 2 multiply layer, another 100 and neuron, another hidden layer, another fully connect output layer that are actually 1 neuron, and that the last layer that have 1 neuron is actually simply because we output a scalar, so there is only 1 degree of freedom. And this is reflected in this code. You can see that there is the first layer, okay, is actually here, and then we multiply. We have 2 multiply layer and then another dense layer. So and then we have another multiply layer, and then the last layer actually have activation function that are linear, and this is actually the output layer that output the energy functional. Okay, so and then basically we just like that we can define the entire architecture for as a class, and we can actually put everything together, and then the neural network design is actually done. Now, this is a Sublux training. So what I mean is that we would use both the gradient data and the original data as the training material. So we need to load the data here, and this is actually the code corresponding to the loading. Okay, so in that, as you can see in the descriptions, we need the data of x and y, and also the gradient of y for supervision. So in this particular case, because we are training an energy functional, the x is what the x mean is actually the volumetric strength and the directoric strength, and the output is y is the energy functional, and then the gradient of y is actually the stress. Okay, so what we did here is basically put the data, we prepare the data and then loading it into for the supervised machine learning. Okay, so I think the code pretty much self-explaining that. And then again, you can actually look at the individual variable, and then some of them have the explanations, and you can actually see what's going on. One thing that I would highly recommend is actually to rescaling the data. That actually help the training, in particular, if you have one set of data that have much sharper gradient or much bigger values than the other, or you're trying to create a multi-objective problem, if you actually did not rescaling the different objective, very likely the loss function that has higher numerical range may be perceived to be more important, and then the other tasks would actually not getting solved. So the rescaling is pretty standard machine learning 101 thing. Basically, we find the range of the data plus and minor, and actually, and then the center of the data we consider it. And then, of course, this is assuming that the data is actually a vector data. So please don't using it for rotation. For example, if you actually have a rotation tensor, you probably can do well. On the other hand, if you actually doing it on the skew symmetric tensor component. Anyway, so this is actually the normalizations. The normalization are actually the one that put into the Sublux training in order to guarantee a better predictions. Okay, so the next thing that we're going to do is the training itself. Again, because we're normalizing it, we need to use the train rule to get the normalized data. And then basically we have a multi-objective problem. We try to minimize the discrepancy between the predict energy and the actual energy. And then we actually also try to make sure that the gradient of it are actually sufficiently close to each other, measured by the L2 norm of the tangent. So this is actually the theory. The corresponding code is actually in this Sublux trainer. So you can think about it. This is actually what we actually implement, and then and this is actually the detailed setup. So there are some details that we need to look at. We need to collect So we need to use the data, and then for all the point cloud, we need to evaluate the energy and also the derivative. And then we're going to put it, and then we need to contain a split between the validation set and the test set and the training set. So in this simple exercise, the data are actually split into two mutually exclusive data. The data that are used for training and then the data that are used for validations. The validations data in this particular case are not used in the training. So there's a split between the two. And we are actually going to compute the loss functions based on the data that are from the training and also from the validation data separately. There are two sets of loss functions, the training loss functions and then the validation functions, so that we can actually evaluate how much overfitting do we have. So general issues of training the problem, or at least the classical way of the machine learning, is that we want to sufficiently regularizing the training process so that the loss functions between the validations and the training are sufficiently close to each other to avoid overfitting. One thing that could be important to remember is that in practice, a lot of time, neural network are on purposely over parameterized, and then there's still a big gap. But sometimes even in the sense of overfitting exists, the task may be still better. The validations loss may still be lower if we are actually giving a sufficiently large neural network. This is kind of like a paradox and from the classical sense, but here we would actually simply measure and observe if there is any overfitting here. So this is actually where we split the data. Okay, so and I think that then the gradient are actually rescale, so you can see the code, and then there's a training. Okay, and then it will output the results. Okay. Now, in order to run it in the Jupyter Notebook, you can run it one by one, or you can run it in all steps. So here, I will just run everything. So if you want to run it, run all the code here at once times all together. What you actually need to do is you click on one time and then just click one more. And then you will see this warning. Okay, this is not a good thing by Google, but by the programmer and a contributor of this short course, my student Ming Xiao, that actually wrote the code. And I'm going to run it. And what you see is the execution time. In here, you can also see in the bottom of the notebook, you can also see what is going on, which cell is getting executed. So it's super convenient for a small problem. Okay, so the tasks that are complete, you can see a tick here, and the tasks that are ongoing is actually, you can actually see it moving along. So this is actually the training part. So essentially what you can see is the optimization problem getting solved by adjusting the weight and then the bias. We will get a different loss functions for the validations and the training. And then depends on how you set it up, it can run forever or you run for a certain amount of time. So this is a tutorial, not the actual productions work. So we will actually cut the training short. So now the training is complete in 54 seconds. That is actually because the data is actually very simple. And you can actually see and then we would actually basically show the results. So here you can see the split between the validation data and the training data. What it shows you is the loss functions. The lower score, the lower the loss function it is, the more success the training is. You can see that even in that setting, there is a little bit difference between the training accuracy and the validation accuracy. There's a really small but visible gap. both for the values loss and also for the gradient loss, but they are very minor because the loss function is plotted in log scale, which indicating that there's the overfitting is not severe. And this is actually not really surprising because we simply try to train any quadratic energy functional, and then the stress strain relationship is linear. Okay, and basically the second derivative is a constant. So you can see the energy functional between the ground truth and the P and Q, and the mean stress and the directory stress that are predicted, and also the ground truth, they're very close to each other. And then we can also load the stress strain curve. Again, this is a linear stress strain relationship, so you see things actually match. So I would also like to say that in real life, the data that we collect are not necessarily perfect. So here I would add a little bit of a small numerical experiment. I will add some random noise in the parametric space just to make things a little bit more confusing. So this is a random noise we add into the energy functional, and then we do the training. So here we see that with negligible noise, we are actually still able to train something pretty great. If you actually add more noise, that may be another story, but you can still start to see a little bit of discrepancy. But in general, when the noise is actually very small, like the one we put in there, it doesn't really affect the learning that much. And this is actually pretty understandable because this is a very easy task. Now, if you want to train a more complex data or experiment with it within that script, that is actually pretty easy. So I would say that, for example, if I want to train a nonlinear energy functional or the energy functional that have coupling, okay, and I want to see what happens, you can simply change the code here. For example, I want to train an energy functional that have coupling between the volumetric string and the directoric string. So here, X and Y are not the input and output, but X is respond to the volumetric string, and Y is the directoric string, and then the return is actually the energy functional. Okay, so here, if I want to make it more complicated, let's say that I have a directoric volumetric coupling. So I would actually write a functional perhaps like this. Actually, physically, it may not make sense. I'm just make something up, and then I'm going to try to train a more complex energy functional. And then what you need to do is that once you make the change, you just need to execute it. And this is in the collaboratory is very simple. You simply need to restart and run all. And then you will lose all the previous data. But then, oh, sorry, I think I make a bug here. Sorry, okay, so also that may be a good to say is to see that. So here I generate a bug accidentally in this tutorial. I lack something, and you can see the syntax error, and you can actually serve the Stack Overflow to see how other people solving it. This is also a very convenient online tools. If you're not familiar with programming at all, or you haven't programmed with stuff for quite some time, you can, if you click on it, you can actually see the support or other people have similar issues that on the Stack Overflows, and then there are answer that potentially could be helpful for you. Those are really practical stuff that could be helpful. So go back to this. I'm going to train the same neural network architecture with a new set of the data. I'm going to create a ground truth thing that are actually rather random, or maybe I make it even more complicated. I'm going to make a random variable, and then I'm going to times a very small values just to see what happens. Or maybe even smaller. Okay, so and then let's see whether that work. Okay, so you can see that, okay, So if this probably doesn't work, and then it will point out the error. So let me take out this. Okay, and then this time I think it should work. Okay, so you see the tick here. This is done. This is done, and I will retrain the whole thing again. You can just look at the part. So we start training. So you can see the revolutions of the training after 10 after 10 iterations, the loss is actually going down, and then this time we probably need to wait a little bit longer. So now when you see the training, when this thing going down, it's probably indicating that it's actually pointing to the right directions that increase the that are actually the neural network are able to tune to the direction where you have less error. You don't see that all the time. Sometimes when you put some neural network there, you may see that a frag a plateau a little bit, or the loose functions doesn't go down at all. Then this is a situation where you need to think about whether to change the architecture, or the training problem is too difficult, or we need to, but all it indicates is that if the validation functions and also the training date, the training loss is not going down, it indicates that the training is not successful. Okay. So this probably is the most difficult part, because you never know, maybe I put more, I actually train a little bit longer, maybe maybe it would optimize again. It depends on whether the training is successful. Also depends on where you are in that parametric space. If the data or the value functions have one minimizer, that would be much easier to train than some data that have a lot of oscillations. Again, because we are not using a pure deterministic gradient based method. If you have a little bit of a local minimizer situation there, you probably can get out because of the stochastic nature of it. So here you can see the results, the training. In general, you can already see the difference in this new data set because of the coupling between the volumetric and directoric part, and also the resultant nonlinearity. The training get a little bit harder, and usually you can see the energy training is easier than the gradient training, which is perhaps not so surprising. And you can see now the ground true energy functional and then the true energy functional. Previously, if you remember, this is linear and you get a straight line, and there's no coupling between the directoric and volumetric coupling. But now in that particular test, you can see the landscape get changed a little bit. Okay. And then you can also see the data now that we are training a nonlinear elasticity model. And that nonlinear elasticity model is not just nonlinear, but have volumetric and directoric coupling. You can see the energy functional is still have a good property as increasing the strength, the energy increase, which is actually an important criteria. But you can also seeing that the mean stress and the directoric stress are now nonlinear. Okay, so basically in that script, you can change any isotropic energy functional. I can guarantee that it cannot change any anisotropic energy functional, because you cannot change anything anisotropic with two invariants. I think that is obvious. But in principle, you can increase the parametric space and then you train a generic anisotropic energy functional for small string, for large string problem. And one thing you can see is that in this methodology, I never have to come up with a particular set of equations that presumably may work and then implement it in a finite element code or whatever code I have, and then solving the inverse problem to find the shear modulus or bulk modulus. Okay, so one important thing is that in this particular case, the data set is only generated for one circuit. And in the training process, it merged two of the problem together. The problem to compose an energy functional and the inverse problem to identify the material parameter. In this machine learning case, there is no material parameter to identify because we simply are trying to only generate a circuit for one particular model. This is also an important difference between writing a neural network energy functional and a handcraft model. In a handcraft model, you are never going to write one single model for one circuit. It's going to be a humanist effort, because if you're dealing with natural material or manufactured material that have trillions or maybe billions of different microstructure. But in the machine learning, because the two processes are merged together, if you have an image, and then you can run direct numerical simulations, you can probably create a model that are tutored specifically for one particular RVE. There are more work that attempt to resemble a classical constitutive model that can create a family of a constitutive law for different microstructure, but that would be outside the scope of this tutorial. I hope that this is useful in a practical sense. And I think that I will confess that we did not use any advanced technique in machine learning, but even the simple thing, if we execute properly, could be useful, at least for training an energy functional. Okay, so thank you very much. And I will continue with the next tutorial very soon. Thank you.